Hello, everyone. I'm Jiangguo. I'm a bioengineering PhD student at Rice University under Dr. Oleg Igoshin. Today, I'm going to talk about applying deep learning method to the quantification of Myxococcus Xanthus aggregation and rippling behaviors. The background of my project lies in the emergent behaviors. The emergent behaviors refer to the properties of a complex system that does not exist in the individual system part, but it comes out with their interactions. So such self-organized behaviors are widely exist in physical or biological systems. As illustrated here, you can see the growth of ice crystal or the flocking behavior of birds. So they are also widespread in cellular level. So here, as biologists, we pick Myxococcus xanthus as the model system to study the self-organization. It is a kind of unicellular organism, but they can self-organize into complex structures. As shown on the left, Myxococcus xanthus preying on an E. coli colony. So while they're preying, they form the moving waves called ripples. And when starving, they start to self-organize into streams and get together to form aggregates, large amounts of hundreds of thousands of cells. And finally, they get to the round, non-motile spores. So in order to analyze these patterns, we use different microscopes to observe. These two are two different kinds of microscopes that are commonly used. One is the phase contrast or the bright field microscope. The other is the fluorescent microscope. So although the phase contrast microscope enhances the contrast, you can see it also introduces some artifacts like the halos at the boundary of the objects or the shade off in the middle of the objects. So this may obscure the object of interest. So it is better if we can have the fluorescent image because the cells have higher intensity than the background, so that we can even estimate the cell density from the fluorescent image. So first, let's do some analysis on the aggregate segmentation. So using the threshold-based method, we can find that in the phase contrast image, most of the mature aggregates are well defined by their high intensity boundaries, and the middle can be filled by our algorithm. So they're well segmented. However, for some immature aggregates, the boundaries are not well defined, so they cannot be well segmented. It is different on the fluorescent image because no matter mature or not, they have higher intensity than the background, so they can be segmented. So the fluorescent images outperforms phase contrast images in aggregate segmentation. Then we move on to another pattern called stream. The stream can be visualized with histogram equalization because it can enhance the background intensity. After histogram equalization, and we superimpose the cell trajectory in 50 minutes. These are shown in red on these images. And as you can see, under these red trajectories, on the fluorescent image, the cell intensity is high. The image intensity is higher. However, on the phase contrast image, under these cell trajectories, the pixel intensity is neither higher nor lower than the surrounding space, which means we cannot visualize the streams on phase contrast image. So therefore, fluorescent images also outperforms phase contrast images in visualization of streams between the aggregates. However, we do not always have fluorescent images because first, it requires cell engineering to introduce the fluorescent protein. Second, the long-time exposure to the fluorescent light may lead to phototoxicity. So the phase contrast image is easier to produce. So is there a way to take advantage of both of these methodologies? So we aim to develop a method to transform the phase contrast image to the fluorescent image. As we know, deep learning is promising in high-resolution image transformation. Here are two examples. First, it can transform the map to area photo, which means it's able to recover the detailed information. The other one is it can transform the day photo to the night photo with a given night photo of another view, which means the model is able to separate and combine the structure information and the style information. So we start from the state-of-the-art model, Pix2Pix HD, and learn how it works. So first, it trains a smaller residual network. It takes in the low-resolution images, and then after we have trained this G1, the feature map is fed into the high-resolution model, G2. And by training them together, the model is able to learn the coarse grain information from G1 and the detailed information from G2. So our task is a similar case. By changing the input to the phase contrast image and the output to the fluorescent image, we are able to apply the model to our case. Also, for this high-resolution image transformation, we also designed the multi-level discriminator. So the multi-level discriminator discriminates the output images at different resolution levels. And we also use the feature matching loss to compare the features on different layers of the discriminator. Okay, so after training the model for 3,000 epochs on 9 movies taken each taken in 24 hours, we can get the result. The synthesized image can recover the aggregates at the correct position. As we know, if we apply histogram equalization, we can visualize the stream. However, in some area of the synthesized image, the streams are blurry, which means that the Pix2Pix HD cannot recover streams very well. Is there any idea to improve the model? So we start from the previous Pix2Pix HD and introduce an extra output with the histogram equalized image. So although we have 2 outputs, most of the feature layers are shared so that the model is able to learn both aggregate information and stream information. And we named it as Pix2Pix HD-HE. The result here shows that we can not only recover the stream information, not only recover the aggregate information, but also stream information, even if it is blurry in the previous Pix2Pix HD model. So the result shows that Pix2Pix HD-HE can recover both aggregate and stream information. We also have some quantitative analysis in our published paper. You can search for it by the name of this presentation. And next, we want to compare the aggregates segmented from different images. So using the same segmentation method, the comparison result is shown below. So the red indicates that the aggregate red area is the aggregate segmented from the compared image, but not in the real image. And the orange shows the aggregates in the real image, but not in the compared image. So as you can see, there are a lot of differences between the phase contrast image and fluorescent image. However, through our model conversion, these two aggregates matches, and because you can see there are a lot of overlap, so which means that we can we have good agreement in the positions and sizes of aggregates segmented from synthesized image, but there's some small variations on the boundaries. So we want to evaluate how much variation is there. So we take the center points of each aggregate and calculate the displacement. And then we calculate the relative area of each aggregate. So if the relative area is close to 1, it means that they match with each other. The result shows that the aggregate center displacement for the synthesized image has a mean value around 7 microns. So 7 microns is the length of the myxo cell. So it is a good result. And on the right shows the relative area. As we can see, the synthesized image has a relative area around 1. So the next, what if we are interested in more self-organization patterns of myxos? For example, the way the ripples. Here, you can see on the phase contrast image of ripple, we sometimes cannot see the ripples. However, the ripple is really clear on the fluorescent image. So this conversion will really help our study. However, when we applied our model directly on this case, we can synthesize a fluorescent-like image, but there's no rippling pattern. So by taking the transfer learning idea, we further train the model on the rippling pattern, and we can see that the rippling pattern occurs with further training. We can calculate the wavelengths by Fourier transformation, and we can see that the synthesized image with further training can get the same wavelengths as the real fluorescent image. In conclusion, our model can successfully transform high-resolution phase contrast aggregate images to synthesized fluorescent images of Myxococcus xanthus, and with additional training, the model can be transferred to rippling patterns. So the further direction, our model can assist other high-resolution biological image transformation tasks. And it can also help us with the next step, feature extraction task. And that's all of my presentation today. Thank you.